Okay, chapter 11 is wave phenomena. This is a continuation from the earlier waves chapter. So first we studied about traveling waves and wave properties of traveling waves. This chapter starts off with a description and understanding of standing waves or stationary waves. Then part 2 is a discussion on Doppler effect. Then we have three basic wave properties or wave phenomena of diffraction, refraction and reflection. This was discussed in the earlier portion, but over here diffraction has been elaborated further in the HL portion. Then we have the resolution of two waves, and we also have the last part, which is about polarization. So we'll start off with standing waves. So basically the basic understanding of standing waves is that when you have, let's say, a pulse traveling in a certain direction and there's a fixed point at the other end, when this pulse reaches this end, it will reflect and it will change its phase by pi. So it will reflect and reverse its shape. Okay. So if this other end were to be fixed over here, and basically bringing the 2 points close together, we would have the pulse and its reflection interfering with each other. Okay, the interference of the wave and its reflection is what causes the standing wave to be set up. Okay, now this is how a one-dimensional standing wave is set up. This kind of a shape is called the fundamental harmonic of a standing wave. There could also be other forms of a standing wave whereby you have two pulses, or an upward pulse and a downward pulse, like that. And when this one reflects off and interferes with its reflection, they will set up a standing wave as well. So, 11.1.2 on page 3 explains how this happens basically when the reflection is pi out of phase and the wave itself and the reflection interfere to set up a standing wave. Now, just like any other wave, this wave has energy, but the difference between a traveling wave and a standing wave is that the energy is not propagated. The energy is trapped within the fixed ends of the standing wave. So energy is not propagated. Okay. But this does not mean that there is no energy in a standing wave. A standing wave has energy like any other wave. Okay. 11.1.1 here tells you how standing waves are the result of superposition of two waves with the same speed, frequency and amplitude traveling in opposite directions. That means a wave and its own reflection. Alright, so discuss the modes of vibrations of strings and air in open and in closed pipes. Now, the two examples that will be discussed mostly in IB of standing waves are a string fixed between 2 points, okay, and also a standing wave set up in a pipe because of air. So a longitudinal wave setting up a standing wave in an open pipe or a closed pipe. So we'll see how that works. Firstly, a string between two fixed ends. So like we mentioned, this is one mode, or the fundamental mode of a standing wave. Let's say that the length of this string is L, or the length of the setup over here is L. Now, velocity. Okay, so we have the velocity, wavelength and frequency. Now, the velocity of this wave will depend only on the medium, the length of the string, and also the medium that the string is actually vibrating in. So velocity over here in this case, let's assume that it is v. Okay. Wavelength of this wave. So if we were to draw this entire wave structure, okay, the wavelength would be something of this sort. Okay. So we can see that only the length of this structure here is just half a wavelength. which means that the wavelength is 2L. Okay, and by the formula V equals lambda f, we have f equals V over 2L. Right? Now the next setup, okay, some characteristics of a standing wave first. So when this string vibrates, we can see that each point on the string has a different amplitude. This point here is going to oscillate this much, whereas this point here will oscillate a lot. And the points at the ends will not oscillate at all. So these points that don't oscillate are called nodes. Okay? The point here which oscillates the maximum is called an antinode. Okay? Now, when the string is oscillating, all the points are going to be at the topmost position, then all of them together will be at the equilibrium position, and all of them will also now be at the bottommost position. So in this case, you can see that all points are actually in phase in the wave, right? So, but there could also be a case which we'll see in the second harmonic, that the wave is like this. So in this case, you have another node over here which does not oscillate. You have two antinodes here, and all points from here to here, all these points are going to oscillate in phase, and all these points will oscillate in phase. But each of them, this section of the points and this section of the points are exactly out of phase. So you can see that the points cannot have any kind of phase difference. They can either have a phase difference of 0. So phase difference can only either be 0, okay, or pi. So these have a phase difference of pi with these points. Okay, so this is one difference between a standing wave and a traveling wave. In a traveling wave, points can have a phase difference of anything between 0 and 2 pi. Okay. Another difference that we just talked about between traveling waves and standing waves is that in standing waves, each point has a different amplitude. But in a traveling wave, all points have the same amplitude. Okay. So now we have the fundamental mode over here. Let's talk about the next possible mode where we have nodes at the ends. We cannot have an antinode at the end because it's a fixed point. So it will look something like that. Okay, and when it oscillates, this would be the other phase of oscillation. Now, in this we can see we have three nodes over here. This entire structure here is one wave, right? Firstly, the speed would still be the same. The wavelength now is just L, and the frequency would become V over L. Okay. So, in the third mode over here would then be like that. Okay, and the oscillating phase, the other phase of oscillation will look something like that. Over here we have 4 nodes, okay, and 3 antinodes. And if we look at this, now how do we actually go about understanding what's the wavelength? Let's make a line here at each node. I've divided L into 1, 2 and 3 parts, and I want 2 parts out of that to complete one wavelength, right? So the wavelength will be 2 parts out of 3 of L. Okay, and over here we'll have 3V over 2L as the frequency. Okay, so now we see a pattern and we can recognize a pattern over here. Over here, this is 2L, this is V over 2L, this here is 2 times V over 2L, this is 3 times V over 2L, alright? This is 2L, this is 2L by 2, okay? This is 2L by 3, right? So if you see and go forward and draw more modes, you will notice that lambda for a string between 2 fixed ends is given by 2L over n, okay, lambda n, where n is the mode of oscillation. So mode of oscillation is also called the harmonic, Okay, so this here is called the first harmonic. This is called the second harmonic. This is called the third harmonic. How do you recognize first harmonic? A first harmonic has 2 nodes. A second harmonic has 3 nodes. A third harmonic has 4 nodes, etc. Okay? Or you can just talk about the antinode. The first harmonic has 1 antinode. A second harmonic has 2 antinodes. And a third harmonic has 3 antinodes. And a general formula for F then would be n times V over 2L. Okay? And also this frequency here is called the fundamental frequency. Okay? This is the frequency of the second harmonic. This is the frequency of the third harmonic, etc. Okay? So you should notice that this one will always be 2 times the fundamental frequency. The third harmonic frequency will be 3 times the fundamental frequency, and so on and so forth. Okay? Now, another situation can be when we are talking about a pipe. So first let's consider a pipe with 2 open ends. So a standing wave can be set up in an open pipe with sound waves. Okay? Why I'm considering a pipe with 2 open ends first is because this case is pretty similar to the string in between 2 fixed points. Okay? So, however, in this case, you cannot have nodes towards the ends. In standing waves, a node would correspond to a point where the air particles or the air molecules are not oscillating at all. Such a point can only happen at a closed surface where the air molecules are reflecting off. Okay? So these are not closed surfaces, these are open surfaces, and in order to set up a standing wave here, we would have an antinode setup. Okay? An antinode setup where the particles would be oscillating the maximum. Alright? So if you have an antinode here and an antinode here, the first mode of vibration can look like this. Okay, you have an antinode, node, antinode. Okay? So there's a node here, antinode and antinode. Again, you can see that this L is half a wavelength. Why? Because if I extrapolate this, I would have the same length over here. So this L is half a wavelength, so lambda is 2L. Okay? Again, my frequency becomes V over 2L, where the velocity is V. Okay? Velocity here is this speed of sound in air. Okay? My second harmonic, again, will look something like this. Okay? Okay? And my third harmonic would look like that. Again, you can see here, this entire thing is L or 2L by 2, and over here, if you want to determine how much is one wavelength, I'm going to draw lines at each node and antinode. It becomes easier to do it that way. Now I have 1, 2, 3, 4, 5, 6 parts, and I need 1, 2, 3 and 4 parts out of that in order to get one wavelength. So 4 parts out of 6 of L is 2L over 3. Okay? So you can see this case is pretty similar to the string with 2 fixed ends. And the formulae also remain the same.